So now let's look at example number 1 related to shear stress and viscosity. So here we have a 1 meter by 1 meter board that weighs 25 Newton, slides down an inclined ramp. So the ramp has a slope of 20 degrees with a velocity, a terminal velocity of 2 centimeters per second. The board is separated from the ramp by a thin film of oil with viscosity 0.05 Newton second per meter squared. So the question says that we need to declare the H effect, and then we are asked to calculate the spacing between the board and the ramp. I always start with drawing a schematic diagram where I'm going to put all the informations given. So basically we have a ramp. So the ramp is at the angle theta, which is equal to 20 degrees, right? So we have a block. We have a block. So the block is actually moving down at a constant velocity, which is equal to V, and it's equal to 2 centimeters per second. And then between the block and the ramp, we have spacings. Let's call that one H, which is unknown. And then this gap here is being filled with fluid, which is oil, which has viscosity equal to 0.05 Newton second per meter squared. And then the area of this block, the one which is actually touching the fluid, which is actually 1 meter by 1 meter. And then also given that the weight of this 25 Newton. So the questions also ask us to neglect H effect. So that means that we're going to assume that everywhere on the surfaces of the board which is touching the oil, the shear stress are all the same. So we asked to find H. Okay, so now let us draw a free body diagram. So consider free body diagram of the board. So if I draw the board again, so I draw it bigger now. Okay, so I can, so this is angle theta. So there's a weight acting downward, which is equal to W. So I can resolve this to two components. That way, this is W, so this is W sine theta. That's W sine theta. And then this one here is actually W cos theta. So now, on the surface of the board, which is touching the oil, there will be shear stress, which is trying to resist the motion. So I've called this as Fs. So F shear, so Fs. Now, of course, I would have also the normal force, the normal force, right? So if we balance these forces in the directions which is perpendicular to the ramp, so F normal is equal to W cos theta, right? But I can also balance the forces in the direction which is parallel to the board. Balance the forces parallel to the direction of motion, parallel to the ramp. So I can write W sine theta, which is this way, which will be balanced by F shear, since this is moving at the constant velocity. Basically, it is actually in static equilibrium. So that's equal to F shear. Right. But we know that force is actually equal to the shear stress multiplied by the area. Right. For a fluid, shear stress using the Newton's law of viscosity is actually mu dV by dy multiplied by A. So now if we consider the region here or the region here, if I draw it bigger, I can see that it's moving at a velocity v, right? Whereas, so let's say this is the ramp, so this is the board, so this is actually moving like that. So this is actually a straight line, and this is h, right? So we can write that w sine theta is equal to mu v over h. Okay, the velocity gradient is v over h multiplied by area, right? So I can rearrange that. So what I have is actually is equal to mu v a over w sine theta. Put the value in. Viscosity is equal to 0.05. Velocity is given is equal to 2 centimeter per second, so 2 times 10 to minus 2. And then the area is 1 times 1 meter. And the weight is actually equal to 25 Newton, and then sine 20. So that gives me h is actually equal to 0.00012 meter. Okay, or in millimeter, that's actually equal to 0.12 millimeter. Okay, so the thickness of this oil is equal to 0.12 millimeter. The next examples that we're going to look at will be slightly more complicated, because now the shear stress is not constant on all parts of the surfaces which is in touch with the fluids. So here we have a device which is shown here, which consists of a disc. So the disc is rotated by a shaft. So the disc is positioned very close to a solid boundary, and between the disc and the boundary there is an oil, a viscous oil. So the oil viscosity is given is 0.01 Newton second per meter squared, and the spacing is 2 millimeters. So now we are given the spacing. So now if the rate of rotations is 5 radian per second and the diameter of the disc is 10 centimeter, so we ask calculate the torque required to rotate the disc. So here, if you think about it, we have a disc which is in touch with the liquid and oil at the bottom, and it is rotating. So when it is stationary and you start to rotate the disc, it will accelerate up to a point whereby the disc has achieved terminal velocity, meaning that it is now rotating at a constant rotation speed. And at that point, the shear stress or the torque produced because of the existence of the fluid at the bottom is balanced exactly with the torque that we apply in order to rotate the disc. Let's draw a schematic diagram again. Let's write down everything that we know. So it's a shaft, and then at the end there is a disc, circular disc. Then it is actually in touch with the surface, and the diameter of the disc is equal to d, which is equal to 10 centimeter. Then there's an oil, and the thickness of the oil is constant, is equal to 2 millimeter, and then the shaft is actually rotating at omega, which is equal to 5 radian per second. And then the oil here, the viscosity of the oil is equal to 0.01 Newton second per meter squared. I can also observe that from the bottom, so I have this like that. So it is actually rotating at omega. So we asked to find the torque, and perhaps we can also find the power required in order to rotate the disc. Okay, now, so let us consider any point on the disc. Let's say I just consider this point here. So whereby the distance from the shaft is equal to r. The rate of rotation is omega, so the velocity here is actually equal to omega r. So if we were to consider the shear stress there, shear stress at this point here, let's say I call this one point x, shear stress at point x is actually equal to mu dv by dy. If I were to look from this view, what I can see, looking at this point alone, what I can see is actually, so let's say this is this surface here, right? And if I were to consider the velocity gradient, it will be a constant gradient whereby the velocity here is equal to omega r and the thickness will be h. So this is actually equal to mu omega r divided by h, right? So that is shear stress at this point here. And then we can also observe that the shear stress is actually a function of r. So it is not constant. At a point which is very close to the center of rotation, the velocity will be small, so hence the shear stress is small. Far from the center of rotations, the velocity will be high, so the shear stress will be high as well. So it is not constant everywhere on the disk. And because of that, in order for us to calculate the total torque later on, so we need to first of all calculate the shear stress. We're going to have to do some integrations, right? But we know that anywhere which has fixed value of r will have the same velocity. So we can use that in order to determine our kind of like elemental element. And then from there, we can obtain an expressions for the shear stress for the elemental element, and then the torque for the elemental element. And then we can integrate in order to calculate the torque for the whole of the surfaces. If I draw again, so this is the disk. So this is the center of rotations. So if I consider elemental element like that, whereby the distance from the center of rotation is r, and thickness there is equal to dr. So I say consider torque on elemental ring. So this is the elemental ring. The formula for the torque is always force multiplied by arm's radius. So it is actually dF multiplied by r. So where dF is actually the force on this. But if you consider dF, the force actually here, that's actually equal to tau multiplied by dA, where dA is actually this area. So if we open this up, what is dA actually? So this is dr, and the length of this is actually the perimeter, so it's 2 pi r. So we have dA is actually equal to 2 pi r dr, right? But we know already the expression for tau, and tau is actually equal to mu omega r over h. So now I substitute everything in these expressions. So now we can obtain the expression for the torque for the elemental ring, which is equal to dF. dF is tau dA. Tau is mu omega r over h. dA is 2 pi r dr. That's dF. And then multiply by r. So now we get the expression for that. So if I rearrange that, so I have the torque. So it's 2 pi mu omega divided by h. So I have 1, 2, 3 r cubed dr. So that's actually expression for the torque on this small ring here. So our next task to calculate the torque for the whole of this. So what we need to do now, so from there we can obtain the total torque for whole surface of this, we need to integrate them, right? So it will be equal to 2 pi mu omega over h 0 to r cubed dr. Okay, so if we look at this here, so we need to integrate from r equal to 0. So r equal to 0, we just cover that. And then when r increases, so it will slowly cover the whole of these surfaces, right? So this is r equal to 0 there, and then this is r is equal to the radius of the disc itself. So you will obtain the top on the whole of the surfaces if we do these integrations, right? So if we integrate this, what we get, so since it's just a constant, so 2 pi mu omega over h, so we have r for 4 over 4 from 0 to r. So we have that's equal to 2 pi mu omega over h, r for 4 over 4. So now if we change that into d, so we have 2 pi mu omega over h. So r is actually equal to d over 2, so 1 over 4. So d over 2 to the power of 4. That actually gives me expression for that. So 2 pi mu omega over h. So d to the power of 4 over 4 times 16. So this is 2. So I have expression for the torque. So which is pi mu omega d to the power of 4 over 32h. So now I can put the numbers in. So that's pi mu is equal to, given as 0.01, omega is actually 5 radian per second. The diameter is equal to 10 centimeters, so it's 0.1 meter to the power of 4 over 32, and h is actually equal to 2 millimeters, so 2 times 10 to the minus 3, so that gives me about equal to 2.45 times 10 to the minus 4 Newton meter. That's the unit of that. So if we are also asked to calculate the power is torque multiplied by omega. So easily just put everything there, 2.45 times 10 to the minus 4 times the omega is 5 radian. So we have a value of 0.001225 watt. Okay. So the next example is very similar to the previous one. The only difference is that both sides of the disk, the top and bottoms of the disk, are enclosed in a container. So top and bottoms are actually in touch with the viscous fluid. So we have to consider the torque caused by the fluid at the bottom as well as at the top. So basically it's just double. So we have already calculated just now the value for the torque at the bottom. So we just need to multiply by 2. So let's do this very quickly here. So example 3. So we draw schematic diagram again. We have a disc which is actually connected to a shaft, and the whole of this is actually being enclosed in the container. So we're going to neglect the edge effect again. So the thickness of the oil on both sides equal to S, and then the diameter is actually equal to D again, and then there is oil here, and viscosity is equal to mu Newton second per meter squared. Okay, it is actually rotating at omega radian per second. So you're asked to find the expression for torque. So consider elemental ring element again, like what we did in the previous case. So basically, just consider one side, okay? This just to repeat what we did previously. So this is the elemental ring, right? R, dr, if you consider the force there on that elemental element, and then the area there, dA is actually 2 pi r dr. So we write down the top of that. So it's actually equal to dfr. df is actually equal to tau dar, and then we know that tau is actually equal to mu omega r over s. dA is 2 pi r dr r, right? You get the expression for the torque, which is 2 pi mu omega over s r cubed dr, right? So quickly do the integrations like what we did earlier. So torque 2 pi mu omega over s from 0 to r, right? R cubed dr, so 2 pi mu omega over s r of 4 over 4 from 0 to r. So you have 2 pi mu omega over s r of 4 over 4, right? So you change that to d, so that gives us torque is actually equal to 5 mu omega d to the power of 4 over 32s, right? That's a torque on one surface, either at the top or at the bottom. So the total torque will be top plus torque bottom, which is basically just 2 times torque bottom. We ignore the edge effect and also the effect of the shaft, right? So the total torque, so just 2 times this, so we have pi mu omega d to the power 4 over 16s. Straightforward.